Hi, my name is Caterina and this is the talk for perfectly parallel fairness certification of neural networks. Nowadays, we are seeing machine learning software invading pretty much every aspect of our society. We have examples in criminal justice, in hiring, in finance, and even in healthcare. At the same time, however, concerns are rising on whether we can actually trust this kind of software. One of the concerns is whether this software is fair or is perpetuating bias originally present in the data used to train it, or even introducing new bias. Software that we use almost daily is biased. You can see here a biased translation in Google Translate from English to French. And there are even more examples again in criminal justice, in hiring and healthcare. Given all this, it's really critical now to be able to certify fairness for machine learning systems. The machine learning systems that we focus on in this talk are feed-forward neural networks used for classification of tabular data. These are increasingly used for very large datasets with rows in the order of billions, and data that comes in batches over time. We will use a simple running example of a credit screening neural network that takes as input the amount of credit requested and the age of the person making the request, and decides whether the credit is approved or denied. In particular, in this talk, we will focus on neural networks with ReLU activation functions. That is, neural networks in which the values of the nodes in the hidden layers are the maximum between 0 and the linear combination of the values of the nodes in the previous layer. I invite you to check out our paper to see a discussion on how our approach generalizes to other activation functions. And the output layer of the neural network contains one node for each class in the classification, and the chosen class is given by the node with the maximum value. And next, when we talk about fairness, we have tons of definitions in the literature. And so for this work, we have chosen a definition originally proposed by Gallotra and others at the FSC 2017. This definition, we call it dependency fairness, and states that the classification of a neural network is independent of the values of the sensitive input features. Our approach is parametric in the choice of the sensitive features. So in our credit screening example, for instance, let's assume that age is the sensitive feature. So if we have a credit request made by a young person and the request is approved, the same request made by an older person should also be approved. If not, we have bias because the only difference between the two input data points is the age, which should not be ground for discrimination. The reason why we chose this notion of fairness is that it is amenable to static analysis and it is stronger than group-based notions of fairness. Finally, for certification, we use static analysis, and in particular, static analysis by abstract interpretation, which nowadays is an integral part of the development of traditional critical software and offers a good trade-off between scalability and precision of the analysis. Let's expand our toy example into an actual neural network. This can also be seen as a simple sequential program in which each node of the neural network corresponds to a program variable, and the ReLU activation functions are modeled by if statements. The then branch of the if statements models the active status of the ReLU, and the else branch represents the inactive status of the ReLU. Now, one first naive idea for doing static analysis for dependency fairness is to do a backward analysis. We start at the output layer of the neural network with an abstract domain element representing each possible classification, and we proceed backwards to find an over approximation of the regions of the input space that may lead to each classification. At that point, we can project away the value of the sensitive features and check whether we have an intersection between the resulting regions. If there is an intersection, then we have two input data points that only differ for the values of the sensitive feature. because those are the ones that we projected away, and lead to different classifications. This could be a false alarm, a result of the over-approximation, or real bias present in the neural network. Instead, if the intersection is empty, then we know for sure that the neural network is fair. The problem with this approach is that if we want to retain enough precision, we have to consider each path through a ReLU or corresponding if statement separately, and this leads to an exponential explosion. We can see this in our toy example. We start at the end of the program with one abstract domain element for each possible classification. These abstract domain elements become 4 for each classification once we analyze an hidden layer, and 16 once we analyze the next hidden layer, and so on. So you can see that this in practice does not scale because there are too many disjunctions, even in such a small toy neural network. Our solution is instead to first do a forward pre-analysis with a cheap abstract domain. So more specifically, we iteratively partition the input space in a way that I will explain in a moment, and we proceed forward in parallel for each partition. With this pre-analysis, we identify partitions that are already fair because they only lead to one possible classification, and all other partitions are grouped together by activation pattern, that is, according to the activation status of the ReLUs for inputs belonging to those partitions. In fact, it turns out that relatively few activation patterns are generally enough to cover all partitions of the input space. So ReLUs can be always active, always inactive, or without a fixed activation status. When a ReLU has a fixed status, it means that only one branch of the corresponding if statement is actually feasible from that input partition. We then run the backward analysis in parallel for each activation pattern and use the information of the activation status of the ReLUs to prune away some paths. In particular, we fix an upper bound on the number of paths that the backward analysis has to explore. This means that we fix an upper bound on the number of ReLUs that are allowed to not have a fixed activation status in an activation pattern. So, in the pre-analysis, we recursively partition the input space until we are below this upper bound. And to enforce termination, we fix a lower bound on the size of the partitions. If we hit this lower bound, then the analysis will give up on that particular partition. I will not be able to conclude whether the neural network is fair or biased for those inputs. So let's see how this works in our example. As we said, we start with the entire input space. We assume here that the inputs have been scaled between 0 and 1. And we do the forward pre-analysis with a lower bound of 0.25. So the smallest partition size is 1/4 of the entire input space, and upper bound of 2. So at most we allow 2 of the 4 ReLUs in this neural network to have a non-fixed activation status. And as abstract domain, we use the interval abstract domain, which is simple and very cheap, and just maintains an interval of possible values for each program variable. With this configuration, if we run the forward analysis, we find an activation pattern in which none of the ReLUs has a fixed activation status. So we have to partition the input space, and one way to do so is to split the domain in half along the known sensitive input dimensions and proceed again in parallel with the pre-analysis for each of the resulting partitions. Now, for the first partition, we find an activation pattern with 3 active ReLUs, while for the second partition, once again, we find an activation pattern in which none of the ReLUs have a fixed activation status. So we split the second partition further and continue with the pre-analysis. Now, we find an activation pattern with 2 active ReLUs, and once again, an activation pattern without fixed values. At this point, however, the size of this last partition has reached the lower bound, so we have to give up with the analysis on this partition. So on this part of the input space, we will not be able to conclude whether the neural network is fair or biased. We will continue instead with the backward analysis for the other two partitions. Now, the second activation pattern that we found actually subsumes the first. In fact, in the last node in this pattern has a fixed activation status in the first pattern and is not fixed in the second pattern. So we can actually group these partitions together under the second activation pattern and run the backward analysis only once using this second activation pattern. So we start at the end of the program with one abstract domain element for each possible classification, as before. Now these abstract domain elements become 2 instead of 4 as before for each classification once we analyze an hidden layer, and 4 instead of 16 once we analyze the next hidden layer. In the end, we can conclude that for inputs in the first partition, the neural network is fair, while it is biased for some inputs in the second partition because there is an overlap between credit requests that are approved and requests that are denied, and the only difference between them is the age of the person making the request. Note that in general, the bias found by the analysis may be intended or accidental. Our analysis does not aim to address this question. I invite you to check out the paper for the formalization and the soundness proof of our approach, and check out our artifact for the implementation. Now, in the remaining minutes, I will give you a quick overview of the experiments that we conducted. So first of all, we experimented with different configurations of the analysis, different lower and upper bounds, and different domains for the forward analysis. So you don't have to look at all the numbers in this table. Just the key takeaways are, as expected, that if we increase the upper bound or decrease the lower bound, the precision of the analysis improves. And moreover, if we use a more precise forward pre-analysis, the forward analysis itself will be slower, but the overall analysis, the combination of forward and backward analysis, can actually be faster. This is because a more precise forward pre-analysis will save more work from the more expensive backward analysis. Next, we experimented with injecting bias into the data and training neural networks with this bias data. And we showed that our approach was indeed able to detect this injected bias. And we also showed that our approach can be used to answer bias queries relatively to some particular region of the input space. Indeed, in some applications, we might be interested in certifying fairness only in some subset of the input space, and our approach naturally works in these settings as well. Finally, we ran some experiments in scalability. The first one was with respect to the size of the analyzed neural networks. So again, you don't have to look at the numbers in this table. As expected, when we analyze larger neural networks, the scalability degrades. However, something interesting that we noticed is that the scalability degrades less for neural networks that possibly have more hidden layers, but fewer nodes in each of these layers. This is because the activation status of ReLUs in earlier layers can influence the activation status of ReLUs in subsequent layers. And so overall, fewer activation patterns are needed to analyze a larger subset of the input space for these kinds of neural networks. And another interesting observation is that increasing the upper bound, surprisingly, sometimes improves scalability, even though it makes the backward analysis do more work. The last experiment that we conducted was with much larger neural networks, and we concluded that in fact the size of the queried input space much more than the size of the analyzed neural network, is what influences the most the scalability of the analysis. Thanks a lot for your attention. Please check out the paper for all the details, and I'm happy now to answer all your questions.